Good morning, Year 10 mathematicians. Just going to finish the last chapter actually in the Year 10 textbook. It's a handling data chapter, handling data number 4. The first topic is estimating probabilities, and we have to define a new concept called relative frequency, which is used to estimate probabilities. But the good news is it is pretty obvious, so it's easy to remember. So the main thing first, I'm going to define some notation which I'm going to use to try and limit how much I write. So imagine we've got we're doing some sort of experiment, because all probabilities start with an experiment, and an outcome to that experiment I'm going to call the letter A. So A represents an outcome from some probability experiment. That experiment could be something as simple as tossing a coin or choosing a playing card, or it could be something a lot more complicated. Now, other notation is, rather than write out the statement a probability of something happening, you can use the following notation, which is a capital or bold letter P, like so, and that would be read as the probability of A happening, whatever that outcome is, the probability of that outcome happening. So you don't have to write it out in words, you can use these symbols. And then slightly different is if I put A with a dash next to it, that dash is similar to Venn diagrams actually. That's the probability of A not happening. It's called a complement. And both of those probabilities should add up to 1. So probability of something happening plus the probability of something not happening is equal to 1. In other words, if I told you the probability of rolling a 6 on a dice is 1/6, then the probability of not rolling a 6 is 5/6, because they need to add up to 1. But there's another formula now, which is called relative frequency, which is equal to, when you've done an experiment, the number of successes of that experiment divided by the total number of trials, the number of times you actually did the experiment. So, okay, this fraction is the most useful thing today. It is going to be used to find the estimated probability of different events. So e.g. number 1 is a really popular type of experiment they do in GCSE probability questions. It is dropping a piece of toast, and the event is whether it's going to land butter side up or land butter side down. So this person has done this trial 8 times, so dropped a piece of toast 8 times and recorded whether it landed butter side up or butter side down. Now you might want to think, okay, which one is it going to be more likely to land on? Is it going to be 50-50? Well, the answer is we don't know. That's why you have to do an experiment for it if you want to work it out. And this person has recorded the outcomes in a table. And then as you work from left to right, the relative frequency fraction will change. So in the first column, the number of successes over the total number of trials, if you only did this once after the first trial, what would the fraction be? Well, number of successes, well, there was no success. It landed butter side down, so 0 successes over 1 trial. So the relative frequency would be 0 over 1, or just 0. If you did it after the second trials. So now you've got 2 trials. How many successes? Well, there's a tick now, so 1 success. 1 out of 2. And if you kept doing this, 3rd trial, still 1 success, but 3 trials. 4th trial, still 1 success, but 4 trials. 5th trial, now they're up to 2 successes for 5 trials. Another success, 3 out of 6, or a half. Don't need to actually simplify probabilities. Simplify fractions in probabilities is the only area of maths where you don't have to simplify fractions. We're up to 7 trials, but only 3 successes. And we finally finished on 8 trials, which still only has 3 successes. So that would be completing this table for relative frequency. And you can see as you add more trials, the fractions change. The next thing you need to do is plot what's called a relative frequency diagram. So that would be using that table where relative frequency is on the y-axis and the number of trials goes along the x-axis. So 1 trial, you would plot 0 over 1 or 0. 2 trials, you plot a half, so 2 a half. 3 trials, plot a third, which would be, just say it's around about there. 4 trials, a quarter. 5 trials, 2/5, so it's a little bit bigger than a third. 6 trials, a half. 7 trials, 3/7. 8 trials, 3/8. And then if you join the dots effectively, use straight line segments to join the dots. You get what's called a relative frequency diagram. And this gives you a visual interpretation of the probability of what's happening. Now, part C is just a 1 marker in an exam, very simple question, which would be, how could you improve the estimation of the probability? And if you visualize this continuing, me doing more trials, now the amount that the probability goes up and down by, how much it varies, will decrease, and the changes will be more subtle as you would go onto more trials. And effectively, if you could do this for an infinite amount of trials, you would actually end up with a true probability. Obviously, you can't realistically do an infinite amount of trials, so if you just want to improve your estimation, then you just do more trials. Okay, so you complete the experiment more times. So just do more trials would give you an improved estimation. Okay, and that estimated probability would be whatever the relative frequency is for how many trials you do. So my exam tip for you for this is, for probability, you don't need to simplify fractions for probabilities. And the questions I would like you to complete are on page 359. And if you could just do exercise 1, that would be great. It's a lot of wordy questions, so you're going to have to use some of your analytical thinking and common sense to answer these, but it should be relatively straightforward. And that is pretty much it.